thanks to the organizers for inviting me and giving this opportunity. I will try to reach out to the physics community and the mathematics people. So if there's anything too vague mathematically and you want to see more details, please ask me. Or if you want to see more heuristics, more motivation, also please ask me, because this is a bit of an outside project. So I will give analogies. I will describe a lot of analogies between the Archimedean setup, like in the reals, the usual o-minimal setting, and the non-Archimedean setting. So the left-hand side will be for our Archimedean setup. And here I will explain what you can think about without going into too much details about the non-Archimedean setup. In the reals, you have exact measurements. So being close together, you have exact numbers. While in the non-Archimedean case, it's all about orders of magnitude. And the orders of magnitude can be like really big orders of magnitude, but you can also zoom in and look at very small scales. So the orders can go both ways. So you can look at very small local deformations of something or extremely big orders of magnitude. And here, being close together for 2 points, it means that the distance is small. The norm of the difference is small. In a non-Archimedean setting, I look at another field than the real numbers. And by field, I mean a ring with certain properties for addition and multiplication. And my toy example field here, that is a good example already, will be the complex numbers. And then the Laurent series field over the complex numbers. And these are just, they look like power series, t to the I, but they can have some negative, finite number of negative exponents of t as well. So L is an integer. The exponents can go up to plus infinity, and the AI are complex numbers. This is a typical context to do non-Archimedean geometry in. And here, to be close together means that you're highly divisible by a high power of t. So if t to the k divides, this could be the point, divides x, then you say it's close to 0. So you want the difference, if you want to say 2 points are close, you say the difference is divisible by a high power of t. So that gives you a notion of topology also on Cartesian powers of r to the n, or this field to the power n. You get the notion of being close and topology, and you can think about functions, their derivatives for that topology, and so on. So it's an order of magnitude, and you have different behavior, but always you have kind of similar behavior with small tweaks and small difference. For example, you have here a typical triangular inequality, which is well known, that you have just to take the sum. That's a triangular inequality. On this side, with the order of vanishing, or the order of magnitude here, you have something slightly related, but also slightly stronger, actually. So the size is small if you're highly divisible, so the order of vanishing is big. But if you take the sum of two things, the order of vanishing can change, but only in one direction. So in fact, it's the minimum of. So if you're close to 0, you can become closer to 0, and so on. So you get a stronger triangular inequality. There is one important function here, which is very basic, which is the sine function. From r to plus sine 0 if you're 0, and minus.
Yeah, just maybe you should say what you mean by.
Sorry.
Is it something with the formula?
No, I mean, what do I mean? Yeah.
I think you were thinking about the order.
Yeah, here I want the max. No, I want to say that if I'm close to 0, then the norm is also close to 0.
What is the absolute value?
You can take 2 to the minus k, for example. Norm.
This minus it was. Yes.
Yeah. So intuitively, if the norm is close to 0, that means you have a high divisibility. So you have this sine function, which is very basic, but very important, of course, on the reals. What plays its role here? That's a bit surprising. that you can replace just the sign function by something. And let's rewrite first the three choices of sign as a quotient. It's the multiplicative semigroup of the reals divided out by a neighborhood of 1. Namely, I just take the strictly positive reals with multiplication. Then I get the three signs as a quotient of semigroups. Here I do something similar. I take the field as a multiplicative semigroup. So with multiplication, I divide out by a multiplicative sub-semigroup, which is a neighborhood of 1, namely 1 plus t times. So that's small stuff. It's a small ball around 1 that I divide out by. I give this a name. These are all my possible signs. And the mapping to that I call little rv for, and I will explain what it does exactly. It goes from CT to this quotient, which I called RV, and it sends such a power series to the leading term. So this x as above is sent to AL t to the L, where I chose my L so that AL is non-zero. So the occurring first leading term, that's what you remember. This is, of course, a little bit symbolic notation, but this is the only thing you see in this quotient. You see it, you look at that leading term inside this quotient. That's a kind of a stupid analog, you could say, of the sign function. But it helps to explain an analogy between o-minimality on this side and some tameness notion also based on finiteness principles on this side. So this map RV will help to explain that. There is another important situation where you want to do non-Archimedean geometry. That's if you put in the middle the field of rational numbers, then you can choose to go to the real numbers by completing using Cauchy sequences and taking all the limits and completing. But you can also complete in another way and go to the non-Archimedean world, and there you get p-adic numbers where the high divisibility by t is replaced by high divisibility by a prime number p. So p to 1000 is very close to 0, and 1 plus p square is close to 1. So you get similar non-Archimedean behavior as in this field. And you also have this sign, the replacement of the sign map in that field. So we want to have some analog here of a finiteness principle that resembles o-minimality and that is equally flexible and powerful and gives tame geometry and good control for definable functions and definable sets. So for that, let me slightly generalize the concept of a structure. We have seen in several talks what is a structure on R and on R2, or it's a collection of subsets of R to the n. But I will work with other fields as well. So let me just briefly adapt that to say what is a structure on a field. And now I call it K. It's a collection, as we have seen before. There are collections of subsets of K to the n. It's a collection Sn for each n. And you ask it to be stable under certain basic operations. Essentially, what you ask it to be stable by is coordinate projections, as we have seen before, Cartesian products, Boolean combinations, and you require that in Sn you have the algebraically the Zariski closed sets. So you have for any polynomial in n variables, the points, the tuples of solutions, P is in the same, is a polynomial over the same field. So it contains these sets, and you close up under projections and Cartesian products and Boolean combinations, then you have a structure, but maybe in the structure you have a lot more definable sets than just these sets. you can have new functions thrown into the structure. So for some structures, you can call them o-minimal. And I will give a slightly different definition to o-minimality to help you understand the analogy with the minimality notion over here. So the structure on R is called o-minimal. It's just a tweak of the definition. If for every definable set X subset of the line, and here I had this collection of subsets of Rn for each n. Here I take a set in S1, and that I call a definable subset of the line. So it means X belongs to my structure S1. The structure is called all these Sn together. If for every definable set X, and now the finiteness comes in, there exists a finite set CR that controls, in a way, the set X, and think of the endpoints of intervals and isolated points and so on. There exists a finite set C, and in what way does it control X? Such that if you want to test, as a physical experiment, you want to test whether a point X, any given real value, whether or not it belongs to X. So I'll give you a real number. You want to test, does it belong to X, yes or no? It's enough to look at the sign tuple. Look at the finite tuple of these signs, X minus little c in big C. That's a finite tuple in this plus minus or 0. And of course, you can just take the endpoints and the isolated points. Now on this side, I told you this map RV, little RV, is an analog of the sign map. So you do just the same to define what we call Hansel minimality instead of o-minimality. So I will write only the keywords here. Hansel minimality, and you take a structure S on your field K, which is here non-archimedean, and let's say, for simplicity, or as a key example, I work with CT because I need some I cannot work with positive characteristic, for example. So this is a safe example. And then I do the same. There need to exist a finite set C in K. Given any definable set X in K, I need to find a finite set, say, and instead of the sign tuple, I look at this RV tuple. So it's a finite tuple again, and belonging to X or not. So given a definable set X in K, there is a finite set C, and I look at that finite sign tuple. And then I call it kind of Hansel minimality, except there is one technicality. That is, here this finite set C can be taken with extra features. In a way, technically for mathematicians, if X lives in a family or it's defined using some parameters, then C can be obtained in a definable way in the parameters also. And that's some extra feature that you need to build in a bit more technically here, because that's not automatic. For example, if you have a ball and you remove a ball from it, and if that is your, so you have this region, if this is your set X, for the set C, you're obliged to take some point inside this little ball, but here we have to impose a bit technical conditions that this can be done in a definable way. This choice of little c here inside this small ball. But up to this technicalities, this gives the definition of Hansel minimality. Let me give one more analogy.
Minimal, are they supposed to be like the constructible sets and they correspond to the constructible sets of like an Alex space, or like what are What is
No,
the capture?
general, it's more flexible.
Bigger than just the constructible sets?
They are more flexible geometry in the sense that definable functions need not to be piecewise analytic. It's just an axiom here that you have this finiteness built in, but then apart from this finiteness that gives a lot of implications, similar as in the o-minimal case, you can go outside of analytic, or you can go outside of analytic geometry. And what you mentioned is more related to analytic, non-archimedean analytic geometry.
Say that this collection of points determine X via this map? Or are you just saying that X is exactly the preimage is some subset?
Yeah, that's equivalent. That's equivalent, yeah.
It's just writing an union of intervals as a.
Here you have a finite union of intervals and points, because let's say, yeah. Here it's less canonical how to choose your finite set, but here you can take canonically the endpoints. Here, if you fix a sign condition, you say, I want to put this equal to the tuple like plus, minus 0. I fix my sign tuple. Then what is the solution set with all the little x? It's either an interval or empty or a singleton. Something similar here, if you would say, I look at all the little x, which is equal to a given tuple of RV values, then what you get, either an empty set, a singleton, or a ball in the t-adic, in this non-archimedean topology. So you get the ball, a singleton, or empty. So it's really some analogy. Here you have a monotonicity theorem on these solution sets precisely, that functions are piecewise monotone on these intervals. Here you also have an analog of monotonicity on precisely the fibers of the sign conditions here. Yes?
So in this RV, you also record the order, right? It's part.
Yeah.
But I mean, do you allow any preimage? Could I take an order divisible by a prime, or I can. It seems like you're saying I can take any sign condition I want, but it could be like all the others that are divisible by squares. I don't think that would be in your.
Yes, you're right. That's a feature that's built in here. On this set RV, you could have chaotic definable subsets, very Cantor sets or whatever. It could be anything here in your structure that would not destroy Hansel minimality. If you have a Hansel minimal structure, you can add any extra subset you want, like the one you say. It will not destroy the Hansel minimality. So you can enrich the residue field, you can enrich the value group, you can enrich these sign condition sets. That's a feature, yeah. Yeah, which is here you have the same on this finite set of signs. You can consider any subset, but it's of course just a finite. It's a finite set. Yeah, yeah. So what are some examples? Here on the left-hand side, you have the globally subanalytic sets, which are called typically Rn. You can do the same on the non-Archimedean side. You have QP with a subanalytic language, where you have analytic functions restricted to some bounded poles. Or on CT, this key example that we're working with, you can also look at globally subanalytic structure generated by restrictions of analytic functions on balls, in any number of variables also. So these are typical examples of o-minimality here, Hansel minimality here, but you have on both sides, you have more examples.
I think I'm still confused. So you're saying you want really this sign to be equal to a fixed value, and this should be a finite union of this?
No, not a finite union.
So no.
I will scale back a little bit. So if you want to test whether any given point in your field belongs to X or not, you just have to look at this finite tuple, and this will say you yes or no. So if you change X, but you keep the same tuple, you will get the same answer, yes or no.
Yeah.
But this is a finite, this is infinite possibilities. Yeah, you have infinite possibilities. And then I said, on top of that, if you fix a tuple of these conditions, then you get a ball, a singleton, or empty, like there. So yeah, but you have infinitely many tuples that can be tested. Yeah.
this related in some precise way to the notion in Oswald's paper, like his version of like a tame non-archimedean structure?
Yeah, good question. I think Oswald's notion is more related to b-minimality, which was a notion predating Hensel minimality. And I think Oswald uses it more for, I think he uses it for algebraically closed valued fields. While here, this is not an algebraically closed field, QP also not, so it's more flexible. And I think also Oswald wanted to essentially uses it for substructures of the subanalytic or the rigid analytic. So he puts himself in the rigid analytic setting. Okay. Yeah.
Sorry, you said that characteristic 0 is not essential or is essential for your setup?
We need characteristic 0, but it could be mixed characteristic, like in QP. It's
Yeah.
what we call mixed characteristic. Yeah, that's yeah. Okay, this is it for the definitions. Let's now go to some results. First, I can give you some, just verbally, some results. So in the o-minimal side, you know that you have cell decomposition. All the definable functions are piecewise CK. And you have the same here. So all definable functions are piecewise CK. So you have this kind of control up to finite level. But here a deeper result and more recent result is the counting result by Pila-Wilkie from 2006. And the main talk will be, the main issue will be here to adapt that to a Hensel minimal setting. And I will discuss how it relates, also in effective and sharp variance. Partial relation, yeah. So here, if you have a definable subset of Rn, definable, I fix any epsilon bigger than 0. We've seen in previous talks that there then is a constant C equal to C epsilon, depending on epsilon, such that if you look at the transcendental part of X, and that has been defined before, please ask me if you want me to repeat it. But X, the transcendental part, throws away some algebraic part, and you then take Q rational points on that set, and you work in a box. So both the numerators and the denominators are bounded by some number h, so that you get a finite set of test points, rational points in that box. You have to test, do they lie or not on the transcendental part. You count them, and they grow very, very slowly when the box grows, namely c times h to the epsilon. So this gives a finiteness, of course, but also very slow growth coming just from o-minimality, this finiteness condition on the line, on subsets of the line. Yeah, this is what I want to say here. Let's now look at this field, CT. And suppose, yeah, here the condition is o-minimality. Let's now do some color.
Before you go on, here you really think of your spaces as a set of k points.
Yeah.
Can I extend this if I want to work with adding spaces or this kind of thing? Can I extend it to higher order points or this kind of thing?
Yes and no. So here on this side, what I can do, most of the time it works uniformly in k. So I don't have to fix my k, but then it works the k points individually for any k. So yes and no, yeah. So it works usually fixed k, but the meaning of and the content of the things and so on are really in the structures so you specialize to k whenever you want to. Yeah.
You change this. I mean, sorry, you said you fix it. So you can also change the ramification. I mean, you can, the uniformizer, can you take it to be round? I mean, let's say I want to change t to the 1/2.
Yeah, you can do that, but then of course, you can ask various you can ask various questions, and depending on what you ask, you need to work hard or it's automatic. But we have some uniformity in the choice of K, but if K is a subfield of L and you want to compare things in K and L, you have to work a bit extra. But if you, yeah, you have potentially, you have to work a bit extra. So here, let's take X in K to the N and definable in some Hensel minimal structure. And I choose my epsilon, then again there exists a C epsilon. But what do I mean now? I take this transcendental part of X again, which is defined in a completely similar way, slightly tweaking the definition. Maybe it's exactly the same definition if you tweaked it in a good way. But what are the Q rational points here in this field CT? Well, I take actually rational functions over the complex field, and I bound the degree of these rational functions, the T degree of the numerator and the denominator. I bound it by a number little h. And little h should be thought of here as log of big H. So that's an analogy, how you should think about it. And what you can do, this is typically, this is a subset. You have finitely many coordinates up to t to the power h. So it's a subset of a complex vector space, c times h to the n or something. It's a subset of a finite dimensional complex vector space just by looking at the coefficients of these rational functions and seeing them as complex numbers. But it could be an infinite subset, so no way that you could bound the number of it, but you can take some kind of dimension of it. And here you don't take a Zariski dimension in there, you take a kind of topological dimension, meaning that you have a finite to one projection, coordinate projection to some lower dimensional complex vector space, so a topological dimension, and then you bound it by epsilon times h plus the constant c. So this is kind of similar to there, because taking dimension is logarithm then counting in many other situations. Okay, that's one thing you could do. On the p-adics, if you would be, let me do that in the middle, if X would be a subset of QP to the N, then again, because QP is a completion of Q, you could count on X trans and the Q rational points again of H. And you find back again H to the epsilon. So that's a closer analogy even to Pila-Wilkie case.
For which, for Hensel minimal structures?
Yeah, yeah. Let me say, so here I have for Hensel minimal structures, and this is work in progress with Halupchuk and Vermeulen. And let me now discuss a lot of special cases and some generalizations where it's already published and on archive, because this is still almost published, almost on archive. If in this case we are subanalytic, so if X is in QPN, that's a special case of Hensel minimality, then we know in fact a bit more. We know a bit more, and it's documented. Also here, let me explain it here. If X is definable in CT, the subanalytic framework, then we know a bit more. And that was work with Gal and Dimitri, that in fact, this topological dimension is always 0. So this bound would become uninteresting. So in this case, topological dimension is equal to 0 because it's a finite set. It's going to be a finite set. But, so you think, okay, in general, in Hensel minimality, in general, you need this small growth. It can really happen. But in the subanalytic case, it cannot happen. And why is that? That's because the algebraic part that you throw away to form the transcendental part is rather big. Because subanalytic sets when you reduce modulo t to the n or you truncate at t to the n, things tend to become algebraic. You don't truncate, you don't work modulo t to the n. Here it's with exact solutions, but still you have a relation between being in the algebraic part and being being able to live to an exact solution of in the algebraic part and so on. But it can grow arbitrarily fast. It's a finite set, but it can grow fast. The size of it can grow very fast with little h, arbitrarily fast. And that's by a similar example as in Gall's talk with the lacunary. If you form something with a lacunary power series, it's going to be subanalytic, but there are some things that grow very fast on it.
So which is very, I'm confused about which is varying. So the equal zero.
Dimension is zero, but something zero dimensional is finite.
So finite.
Of it, if you count the finite set, it grows arbitrarily fast. Can grow, it could grow very fast.
With the asymptotics, right? There would be one silly thing you could do. You could take a map from C of T to itself of some degree, right? There are probably a lot of those. So that'll give you something for a map of X. You'll get maps from XTR, C of T H, to XTR, C of T, some bigger H, like I don't know, 1 to 2, but like precomposing with like T goes to T squared. Because that asymptotic, like that, I guess that makes. I'm just trying. Yeah, the asymptotic is still okay. The epsilon takes care of that. Yes, yeah. I'll withdraw that.
Is it, so there you can draw a sort of a picture of understanding what this means. Can you also say what this, is there some intuition for this statement? Is this a sort of approximation statement of infinite power series by finite power series? Or how do I have to think about this?
The analogy is here with this example by Poggeri and Pila themselves, that for an analytic curve, you really need the h to the epsilon. It cannot be log h. So that's the analog thing to that you can grow very fast.
I know. I'm back to the general statement.
Topological dimension.
Yeah. Can you give some sort of feeling what this statement means, like the analog of the Pila-Wilkie statement?
Yeah.
The picture or something. Very hard to understand. Yeah, so.
Yes, let me try to do that. No, I can try to do that because in the p-adic case, it works uniformly in P. That allows you to say some things also in positive characteristic. So you can also look at the Laurent series field over a finite field. That's not literally being Hansel minimal, but for large P, you can still say something. And then you can count here inside FPT. This is a finite set again. You can bound the degree, the t degree of the numerators and the denominators. And then you find back the Pila-Wilkie counting. So this is a finite set. So instead of topological dimension now, you count and you find back p to the h times epsilon. So this is, this is really again times constant. And that's more so here you see the capital H, its logarithm is little h, so you really get back the analogy. And here saying that the topological dimension would be bounded by epsilon h and this bound, they are more or less the same. So if you count on something of low dimension over a finite field, you find back that kind of bound. It's more or less the same. So it relates to counting, except that you replaced something by an infinite set, and then you take dimensions.
The question, I think maybe we'll answer my previous question.
Yeah.
X comes from C, from like a variety over C.
No, no.
The X times is just the empty set, right?
No, yeah, in that case, yeah, but that's not an interesting case.
I want to check. I mean, I'm not a logician.
So I just
X is an algebraic variety or defined over C,
yeah,
then the algebraic part would be everything
everything, and then X
in an empty set. Yeah. So indeed, via uniform, this aspect that you work uniformly in the valued field is important, but because it allows you to access other fields that you could not access otherwise, like this FPT. Although some more recent work by Bignamini and Kato, you can also access FPT for some definable sets given by zero low C in other ways. That's just a side remark. What I wanted to add to this is that you can, in CT, you can have a substructure where you have some kind of sharpness or effectivity built in. And this is some work we did with Gal and Dimitri, even before you developed the notion of sharpness, sharp o-minimality. We had some structure here, which I will not define in detail, but with restricted Graphians functions. So there are analytic power series having some extra differential equations, or also more generally a variant of that with Noetherian analytic functions satisfying some Noetherian chain of differential equations. And in both cases, you could say a bit more about this counting. So they are substructures of the subanalytic world. So we had this finiteness. Let me go back to this finiteness in CT. So we look at rational functions in T of bounded T degree. And I said it could grow arbitrarily fast if it's subanalytic, but in these more restrictive settings of Graphians or Noetherian functions, we got that it grows actually polynomially in H. So it's like C times H to some power little k. And this is the analog of Wilkie's conjecture here, because again, if log H is little h, Wilkie's conjecture that's now been solved, Isaac, Bignamini, and Novikov, says that here, if you're Graphian, or even more general than Graphian, you can bound by little h to some power k. You become polynomial in the logarithm. So that analogy was kind of predates here in the non-Archimedean case, it predated the o-minimal case. I don't know if it was an inspiration, but in any case, it's an analogy. And but on this non-Archimedean side, you don't have the full exponential. You only have restricted exponential. So it's not yet, does not go further than the restricted Graphian or the restricted Noetherian case. So what goes into proving these results? In most cases, there is some connection that goes into it, resembling a little bit resolution of singularities. And what does resolution of singularities do? It relates geometric objects to smooth objects. So it's a smoothing of your object, and you try to control it as good as you can. All the aspects of the smooth object and how it relates to your original object. But in this context, resolution of singularities does not work so well. And that's because you need everywhere that it works very nicely in families. And resolution of singularities works well in families for this risky topology, in a generic point in the family, in a generic fiber, you can do resolution and so on. But for a real topology or a p-adic topology, it does not work well in families. So you need another kind of smoothing process. And we are going to relate our original objects with some smooth objects by some parameterizations. So it's not a resolution of singularities in the strict sense, but it's what is called parameterization in the sense of Yomdin, and also maybe in the sense of Gromov, but also in the sense of Pila-Wilkie, as I will recall now. And it is this smoothing process that, again, is developed on both sides, Archimedean and non-archimedean. So it's very important in mathematics in general to relate singular objects to smooth objects. So I think maybe also for physicists, it's nice to see this ingredient. And it's the same paper by Pila-Wilkie from 2006. If you have X and you suppose for simplicity to formulate the result that it's contained in a compact. So let's say it's in this standard compact box inside R to the n. And it's definable in any structure which is o-minimal, definable in an o-minimal structure. Then there exists smoothing maps, and you need just finitely many of them. They go from an open box. The only thing you need to say is the dimension of X. It's a certain number, most n, of course. And then you go from the box of the same dimension. This is your smoothing map. You go to X. And you need finitely many of these. And you want these maps to be nice. So let me be given an integer r, say at least 1. And if the r is bigger, then it becomes even nicer, but maybe you need more maps. I want the VI to be CR maps with small CR norm, moreover. So the CR norm should be bounded by a constant, say by the constant 1. So they are, in a CR sense, they are very smooth and very nice. And together, they cover everything. So the union of the images is X. So it's a piecewise reparameterization of your original set. You can do this very nicely in definable families, which is very important to proceed by several kinds of induction on the dimension and so on. It's very important. I will not state how it goes in families, but in particular, this number is fixed throughout definable families. So these are the key aspects.
Of the images, are they the dimensions of the images also M? Like
not necessarily. Not necessarily. X could have a separate connected component of dimension 1.
Oh.
And you also need to cover that in this formulation. Yeah, that's not important, not so important. So an observation you could do here is that this domain is really a nice box. So it's convex because you have the real topology, you can connect points with real paths and so on. And that allows you to do Taylor approximation on the whole domain of this map. Because the CR norm is small, you can Taylor approximate these functions VI very nicely. Let's now go to a non-Archimedean setting. In your favorite non-Archimedean pencil minimal structure. Yeah.
But this should be uniform in families, right?
Yeah.
I mean, this statement is much easier than the left.
Yeah, this you can prove with resolution of singularities, but it's the uniformity in definable families that is key and that I will not state. I don't state it, but in particular, this n is uniform in the definable family. And that's harder already with resolution of singularity. So here in a Hansel minimal structure, you take a definable set X in a compact box. And a typical compact box mathematically is denoted by the valuation ring to the power n, but you can take any ball, compact ball of your likings. It's definable in a Hansel minimal structure, and I fix the dimension again to be m. And then I do a few small changes here. Here, I take slightly different. I change here a little bit. Namely, I take a domain inside the box of the corresponding dimension, but I cannot rectilinearize the domain so well that it becomes really like a square box like in the reals, but it's some subset of the right dimension. And I add one condition that was automatic in the real case, In the real case, I said you get automatically Taylor approximation for free once you know that the CR norm is small and you have a convex domain. The domain is convex and nice in the reals. In the periodics, you don't get that for free because you don't have convexity. Topology is completely different. So what we do, we ask that we impose it in the result, and we work with each step of the proof, we work to get it, that you have Taylor approximation up to degree R. So what does it mean? It means if you have your function Phi of x, and you compare it with the Taylor polynomial of degree at most R, and you evaluate the Taylor polynomial at the same point, but you compute the Taylor polynomial of that function at some other point, and then you take the difference, you get the size of the derivative, which is at most 1, times the difference of your input points to the power R. So it's a typical kind of candidate formulation of approximation by a Taylor polynomial of degree R, and that's globally on the domain. So for any two tuples, x and y, in the domain, I want to have this Taylor approximation for these x and y.
What does the dimension mean in the non-archimedean setting?
Dimension? You can define it in several ways here. In an o-minimal case, you can define dimension using cell decomposition. You partition your definable set into cells. Each cell has a clear dimension. And here you can do the same in this Hensel minimal case. The sign conditions in the line, they give 3 possibilities: a singleton, a ball, or empty. So a singleton, you call it a cell of type 0. A ball is a cell of type 1. And an empty set is nothing you have to consider. And then you have a cell decomposition where you can do this coordinate after coordinate, and you can again define dimension. That's one way. Another way is to see topologically. You do a coordinate projection, and you want a coordinate projection with finite fibers, but where the image is open, contains an open. Such kind of coordinate projections, and in o-minimal case, you can also do that. Coordinate projection that has finite fibers but open in some lower dimensional space, that gives you description of the dimension. So I have a few minutes. So what are the challenges to prove this smoothing result in the non-Archimedean case? There are 3 challenges compared to the o-minimal setting or compared to the subanalytic setting that we already had. Let me describe the 3 challenges. First of all, here in the real setting, it's enough to know local information in the sense that the CR norm looks locally. At any point, you compute the CR norm, and you have to say it's at most 1. Suppose you could do that in a p-adic case. You know everywhere locally the CR norm is small, but then you want some kind of a global Taylor approximation of the whole piece. So how to go from local to piecewise? That's a real issue in the non-Archimedean setting because of this orders. By the whole setup, it's much more difficult and much more strange to go from local to piecewise with finitely many pieces. That's a challenge to overcome, but this was already overcome also for this to treat QP-an, the subanalytic setting. But now if you go to Hensel minimal instead of just subanalytic, there are 2 new challenges. In QP-an or CT-an, you know that definable functions are piecewise analytic. Now, piecewise given by terms, as in Rn, in QP-an as well, you have piecewise analyticity. And if you have piecewise analyticity, locally. So the first challenge was to go from local to global. So now let's look locally. And if you have a function which is locally analytic, you get two things for free by analyticity. You get local Taylor approximation for free to any given degree that you want, actually. And you get a control on the CR norm for free. Some control on the CR norm, like the Cauchy inequalities. If you know the size of where you live, the analytic function lives locally, and you know the size of the image, you get both these things more or less for free. But in a Hansel minimal setting, you don't have piecewise analyticity. It's an axiomatic finiteness framework. So definable functions, they may not be locally analytic. So you have to work hard to get locally Taylor approximation almost everywhere locally, and to control the CR norm locally, just knowing where you look locally and the size of the image. Comparing these, you have to see how can the CR norm almost everywhere be controlled. So these are three challenges. This is it about the explanation about the smoothenings. And to end my talk in the last minutes, let me go to some open questions or some future directions. First, within the context of Hansel minimality. And then after that, I will switch to an algebraic context with some open questions purely about point counting in an algebraic context. Yeah, it's just a vague open question or motivation. But what about sharp? Is there a framework of sharp or effective Hansel minimality? And that's a big open question. And effective, maybe there is a candidate because the semi-algebraic case, like QP-Alge, it's known to be effective in some forms, but in o-minimal setting, our Alge is known to be sharp, but we don't know that in non-Archimedean case. So that's a question. So what do you want to do with sharp or effective? You want the definitions. What could definitions be for these frameworks? And what would be examples, like QP-Alge or the Pfaffian functions could be examples. And then you want the results. If you have something sharp or something effective, can you make this number n, for example, can you also make it sharp or effective in terms of the complexity that enters the picture? So these are a lot of questions. A whole part of a research program. Okay, I think I lost some of you, but feel free to come back because I switch topic a little bit. And I want to conclude with an open question about point counting on some algebraic objects. And I want to raise this open question because it's another example where geometry and point counting has a close connection. So that's related to the topic of the conference, although it's not related to o-minimality. It's purely algebraic algebraic context, some point counting. So suppose I have a curve in the projective plane, and I assume that it's irreducible and of some degree. And I look in a box. So this projective plane has homogeneous coordinates, x, y, z. I look where these x, y, z are integers, but also in a box, minus b. I use the letter b for the box. B. at least one, say, or two, whatever. These are called rational points of bounded height in the projective plane. And now I want to see what's the number of rational points in this box that lie on my curve. And that's something that Bombieri and Pila also studied at Heat Brown. So I want to see rational points, Q-rational, these are called Q-rational points in the box. And Pila and Bombieri in a small variant, I think in a variant by Heat Brown, but it goes back to Pila and Bombieri, showed that there is a constant depending only on D that you need. And actually, I'm interested today in a special regime where the degree is really large. So let's say first that the degree is bigger than logarithm of B. I'm looking at this regime. And then Pila-Wilkie showed there is an upper bound just depending on D, on the degree, only on the degree. But in fact, with Dittmann, Kastrik, and Nguyen, we showed that you can actually take d to the 4 times a constant not depending on anything. But this is not optimal, because if d is at most b, so in this regime, we found a lower bound, which is d square times another constant, c prime. Worst case lower bound. It does not always hold the lower bound. It's a worst case lower bound, can happen. It happens infinitely many times. And then with Dimitri and Gal, but also with Kato, we found that we have actually this upper bound, d square, but you need to introduce some logarithmic factors, some logs to some power. We have this as an upper bound. But is this upper bound d square always optimal? In fact, it turns out d square is not always optimal for some stupid reasons. And that is that on P2 itself, in this box, there are at most b to the power 3 many points, because you have 3 coordinates, 3 integer coordinates. So if d is bigger than b squared, for example, this becomes a stupid bound. So there is one regime where this lower bound breaks down, and that's exactly, it breaks down as being a lower bound. We don't know it anymore. When d is bigger than b, in this regime, we find another lower bound, namely d times b times a constant. db is smaller than d squared in this regime. And we wonder how to bring these two closer to each other in this regime where d is bigger than b. Then in this regime, db is better than d squared. That's a kind of interesting question, because you can have d squared singular points already. So already, only looking at the singular points, you could find d squared many. But can they live in this box, in this regime? You have this regime, can you have the singular points all in that box? And then there is the smooth points. So the smooth points, they can also be not more than d squared many. But we conjecture that maybe you only need db many in this regime. So that's it becomes a kind of a combinatorial problem. Which irreducible curve contains the most rational points in this regime? So they can be brought closer together, but what is the actual tight exponent of d and b that is needed to bring these closer together? That's a question, open question I would like to end with. And I think in terms of sharpness and effectivity, usually you want polynomial bounds. Here they are polynomial, but in this particular setup, you also want the exact perfect tight exponents to find as optimal. So that's a step with extra control compared to sharpness and polynomial bounds. So that's where I would like to stop. Thank you.
Do you have time for questions?
Do you have examples of non-archimedean with, or even conjecture, what is the unrestricted exponential analog, or what? I mean, what is some next structure to consider after?
Yeah. So do you know the T-convex structures introduced by Lau van den Dries? So these are, you start with an o-minimal structure, which is polynomially bounded, and you take a non-standard model of that. So it becomes a valued field because in a non-standard model, you have infinitesimals, you have infinitely big elements. So you get these orders of magnitude. It becomes non-Archimedean. And if you put on top of that language, the o-minimal language, you put on top of that also the valuation topology, you get what he coined T-convex structure. And that turns out to be Hensel minimal. So every o-minimal structure has some non-standard model which becomes Hensel minimal. So you have a lot of examples, also the quasi-analytic, the non-analytic things, the Chevret things, they can all enter the Hensel minimal framework. So you have a bunch of examples. You can, at each time, you can do these parameterizations results in that setting and so on. But there is one thing that fails that you can never do in a Hensel minimal setting, even not in these non-standard real models, and that is to add an entire exponential. That kills Hensel minimality in some ways. So you can only put fragments of exponential. But nevertheless, you can put large fragments of the exponential so that you really have this growth epsilon h plus a constant that I mentioned for the topological dimension of definable sets. This comes from putting a large piece of the exponential, but the entire exponential is not possible.
This is on a ball or a ball? Yeah. A ball of that kind of arbitrary, doesn't matter how big.
Yeah, bounded.
On the ball.
Yeah. So that's something you cannot do in Hensel minimal structure because what we call the analog of the monotonicity here to the real monotonicity, that breaks down with an entire exponential.
We would be interested, for example, if you could take the ultra product of FPT, and for each FPT take the unrestricted Kravitz exponential, and take the limit of those. But this should be maybe, I mean, okay, without the Kravitz exponential, I guess the ultra product of the FPTs should be something like ultra product of the QPs, right?
Yeah,
it would be the minimal of
nice characteristic. Yeah, yeah.
But then, I mean, maybe one can expect the limit of Kravitz exponentials to be.
And the Kravitz exponentials are defined on the whole field. Yeah, so you also have an Iwasawa logarithm on QP, for example. That's a kind of logarithm defined on the whole of QP. And it could enter the framework of Hensel minimality, but then you need to generalize it a little bit, like when you go from o-minimality to quasi-o-minimality, where every definable set is a countable union of o-minimal situations. If you do that also here, then maybe you can put in Iwasawa logarithm or the Kravitz exponential. Then you can try to do that. But this Iwasawa logarithm has an infinite discrete subset of zeros. And maybe also the Kravitz exponential creates some infinite discrete subsets. I'm not sure.
But it's in the imaginary direction, the Drinfeld analog. I thought if you restrict it really to FPT, maybe it's okay. I don't know.
Okay, yeah. Yeah, it could be interesting to look into.
Okay, so it's very interesting. First time that in the structure, I don't understand the same word of what you're saying. And, other question.
But orders of magnitude should.
Yeah. But anyway, that's how it should be. Are there other questions?
So did you say certainly that if you take C double rate brackets, Laurent, like C, that's C, and like something like that, then this topological dimension thing becomes like 0 always?
Yeah.
Are there, do you have explicit examples where it's not like that?
Yeah.
And in those examples, like, you know something, like, is it still the case that like the sizes of the fibers of like this like projection map can grow like very fast?
No, the size of the fibers to calculate the topological dimension, you control also the size of the fibers for these projections to low dimensional spaces. And an example is on RT to RT, you put the fragment of the exponential that is on a large ball. You put the exponential on a large ball so that on the residue field, you also get the whole exponential on the residue field level. And then you get these transcendental parts which are bigger, infinite transcendental parts of your definable set. The graph, you take the graph and then that's a definable set with a big transcendental part. That's an example where you have positive topological dimension of the transcendental part of your definable set. And you can have examples where this keeps growing, this topological dimension, when little h grows also. But we can tell you more later. Yeah.